Okay, so let's motivate the section. Motivations.
So is he doing a test review?
Make your dreams come true.
Motivation. I'm graduating.
4, 1, 2. Oh, I could be like a motivational speaker. I could be.
Asian version.
I could be.
The Asian version is crazy.
Like the star you just like question mark, but then you.
Oh yeah!
Okay,
Yeah, totally.
everybody lock in for a second. So, yeah, those kind of suck. If you have to do higher powers of A, you know, this is not an enjoyable experience, and most of you felt that on the first exam, okay?
It
Now,
was great.
here's the thing though. Here's the thing.
Let's do it again.
Well,
The same question.
Same exact question. This is the only
Okay. Where D is diagonal. Diagonal. Do we remember what a diagonal matrix is? Yeah, like the only possible non-zero entries are happening on the diagonal. Okay. So by definition, A is similar to D, right? Because I have explicitly given it as some PDP inverse. And that was like definitionally what we meant by similar. So if I do that, let's take a look here. Let's look at the case of A squared. What I'm doing is I have PDP inverse times PDP inverse. But I know because this associativity, I can take my P and I have D, and I'm going to do the P inverse times the P first, and then I have D and P inverse. What's P inverse P?
The identity matrix.
Good, so PDI, D, P inverse. And what does the identity do? Yeah, nothing basically. So I have two D's in a row, so it's P D squared P inverse. Yes?
Yes.
Yeah?
Yeah.
That's pretty cool. Let's see if that was a coincidence though. What about A cubed? Okay, so A cubed is going to be A, you can think of it as A times A squared. So PDP inverse times, and then now PD squared P inverse, right? Because we're going up by 1. So this is A and this is A squared, so now we're going to A cubed. And then, you know, it doesn't take a genius to go PD. What if I want to do the P inverse P again? Do that first. D squared P inverse. Okay, what does P inverse P go to? PDI D squared P inverse. How does that simplify? PD cubed P inverse. Do we understand?
Yep.
Okay, so why might diagonal matrices be really, really helpful?
Because it's easy to take some high powers.
Super easy to take them into high powers, right? If I can essentially diagonalize A and make it look like some PDP inverse, then ripping this up to high powers is tantamount to just taking the diagonal matrix and ripping the diagonal matrix up to high powers. Why is that even really helpful? Because when you look at what a diagonal matrix even is, so like for example, we can do just like a 3x3 case for an example. If I have a diagonal 3x3, I have something there, something there, something there on the diagonal. It's the main diagonal. Meaning that all I have to do to raise the power, the moment I raise the power to any k, all I'm doing is putting the power like that. And that's all there is to it. Because that only works because of all the rest are zeros.
Yeah.
So this is why we do diagonalization. So if you ever wonder, wow, this sucks, why am I even spending all the time doing this? Well, it's because it's going to let you do this, okay? So don't lose sight of that. Okay, let's do a definition. A square matrix A, a square matrix A is this is the most horrendous word I have ever known. Diagonalizable.
Diagonal.
If A is similar to a diagonal matrix. I mean, basically, this is just putting into words exactly what we just looked at here. That is, so just restating with symbols, if A is equal to some PDP inverse for some invertible P, for some invertible P, and some diagonal matrix D, then the PDP inverse is similarity. This is definition of similar, and then we're just relating it now to a diagonal matrix, so diagonalizable. Okay, so here's the theorem. And most of this lecture is really just doing one example. Okay, anyway. The diagonalization theorem. An n by n matrix A. N by n matrix A is diagonalizable. Diagonalizable. If and only if A has a linearly independent eigenvector. Oh, I totally typoed myself. Okay, A has not just A, but N linearly independent eigenvectors. In fact, if I have A set equal to P dP inverse, where D is diagonal, so with D diagonal, then if and only if the columns of P, are n linearly independent, eigenvectors of my matrix A. And in this case, sorry, I know this is a lot of words, and it's my least favorite part of this lecture. The diagonal entries of my D are eigenvalues of A that correspond respectively to the eigenvectors in P. And then one more definition here. And then we'll get on to the problem. A is diagonalizable if and only if there are enough eigenvectors. There are enough eigenvectors to form a basis of Rn. And we call such a basis, and we get really creative up in here, an eigenvector basis. Was that Prem snorting there in the background? No. It wasn't that funny. Perchance. There is a distinct disadvantage to not having an internal dialogue. Maybe people think I can teach. In reality, I just can't not yap inside of my head. So counterpoint, you just hear my internal dialogue. Okay. So we have a matrix A. It's going to be diagonalizable if we have n linearly independent eigenvectors. I'm not even going to lie with you. That doesn't make any sense. Like, this doesn't make any sense. So if you like words, I don't. And frankly, it's much easier for me to teach this concept through an example than through its definition. So I provide the definition because that's what you paid for, you're in this class, have it in your notes and all that. But realistically, understanding the procedure is going to be way more important than just having that memorized. Okay, so I'll just say that up front. You don't really need to worry about having that text wall in your brain, okay? Just be able to internalize the algorithm that we're going to cover today, and then that's pretty much it for the section, okay? Yeah?
Yeah.
Okay.
Do not erase the big part.
Take a picture with your phone, because I don't want to I don't want to go over time. Okay, we have documentation. In case you're wondering what topology seminar was like, roughly half of it was just entire text walls on an entire whiteboard, and then saying, okay, now that we've established what an object is, let's actually do something with it.
Now let's rotate the object.
Rotate the object. No, that's a little too complicated there. Because that implies this notion of a rotation,
Exactly.
which also implies a space within which the rotation can occur.
Implies the object is rotatable.
Yeah, exactly. So, I mean, I don't know about you, but that's kind of great. The class before a big break is always the funniest because everyone wants to die, myself included. So we're doing so good, guys. We're gonna get through today. Hell or high water. Okay.
Or both.
It's a wording journal, actually.
Sorry.
I will say, you will be kicking yourself in approximately 2 weeks from today if you don't take notes on this example. And I will go, you did not lock in when I told you to lock in on the one thing that in 2 weeks you don't want to have not locked in, okay?
I don't know if you're verbally winking at us right now, but I'm picking up on it.
It's not a challenge? For chance.
Okay. So step one. So so here's a matrix, and I'm too lazy to write it out again. Basically, diagonalize the matrix, okay? What that means is to diagonalize something is to find the invertible P and the D. And then once you find a diagonal matrix and corresponds to your P matrix, then yeah, that's it. You don't really have to do anything else. I wish they would have chosen other conventional variables because I have to be very careful with how I phrase some of these things. Find the eigenvalues. Okay, remember when we were talking about multiplicity? The multiplicity really mattered. So it wasn't just the distinct types of roots, but how many total roots. You'll get to see exactly why in this example. So the first step is always going to be to find the eigenvalues of your matrix, okay? Now, do we remember how the shortcut we developed for that? Okay, well we could do that. I'm talking more like you have the determinant of A minus lambda I, and what's that determinant supposed to equal? Zero, yeah. So
something the basis of something else.
the determinant of my A minus lambda I is supposed to be equal to 0. Now, what is A minus lambda I? Well, copy paste your matrix, and everywhere there's a diagonal entry, subtract lambda from it, okay? So 1 minus lambda minus 3, 3. And then we have 3. Now here's the next diagonal entry, so it's minus 5 minus lambda 3. 3 minus 3. Now here's a diagonal entry, 1 minus lambda. Please do not forget to put the minus lambdas on your diagonal. Okay, and then now we just get to do some horrendously unfun, tedious algebra to get to our characteristic polynomial. Okay, so let's do a 3x3 cofactor expansion. Let's just go across the top. So I'll take my first value, 1 minus lambda. And if I cover up the first row, or the first column and first row, what's left is minus 5 minus lambda, 3 minus 3, and 1 minus lambda. Everybody happy with that? Yeah. I know this is a blast to the past from chapter 3, but let's not forget how cofactor expansion works. Okay, what do we do with cofactor expansions? We now switch the sign, we alternate signs every time. So please don't forget to do that. Now if we're taking this 3, I'm covering up the top row, and now I'm covering up the middle column. So I'm taking the outside wings here. So minus 3, 3, and minus 3, 1 minus lambda. What do I do to the sign? I alternate the sign, plus my term. Okay, what's that one going to be?
Minus 3, 3 minus 5 minus lambda 3.
Good. So what I'm hearing is Sam Patchen is going to do well on the exam.
Yay! Yay!
Yeah?
That's the goal, Scott.
That's the goal.
That's what it was.
Money.
That's trying to hit that leaderboard. I'll get a code name.
Okay, do we remember how to take the determinant for 2x2s?
AD minus
Okay, so I have minus 5 minus lambda, 1 minus lambda, plus 9 minus -9. Minus 3 times minus 3, 1 minus lambda plus 9, plus 3 times minus 9, minus 5 minus lambda times 3. I'm kind of running out of space there.
Right taller, now wider.
Okay, so as much as I hate to do this for style, I'm gonna move the equals over here. 1 minus lambda. If we expand this out now, minus 5 times 1, minus 5 times minus lambda is positive 5. 5 minus 1 is 4. Lambda squared is positive. And then I have the 9. Minus 3 times, and then minus 3 plus 3 lambda, plus 9, plus 3 times minus 9, and then I have, be very careful with the sign, it's negative 3 times negative 5 is positive 15, and negative 3 times negative lambda is plus 3 lambda. 1 minus lambda lambda squared plus 4 lambda. What's 9 minus 5?
4.
Okay, so now notice, check this out. 3 lambda, what does the constant simplify to? Come on, guys. 9 minus 3 is 6. So 3 lambda plus 6. I have 3 lambda plus. Okay? So I have the same exact thing as this. I have minus 3 of them and plus 3 of them. And if they're exactly the same thing, we don't have to worry about that anymore.
What?
You're a genius, bro.
Okay. So then, let's factorize. 1 minus lambda, and then we have lambda plus 2 squared. Yes? Are we all happy? So happy. Now, that tells me that we have what are my eigenvalues? If it's 1 minus lambda, and then lambda plus 2 squared.
You have -2, and -2.
You have 1, minus 2, and minus 2. Why did I repeat minus 2? Is it because I have a stutter?
No, because it's squared.
No, it's because there are 3 eigenvalues.
Would be surprised.
That is step 1. Does step 1 make sense? Could you do step 1?
No.
If I erased this and said find the eigenvalues of A, could you do that?
That's possible.
Well, way to find out.
Could do.
I guess we will find out. We will find out for sure. Okay, step 2.
Alright, let's do this.
Find linearly independent eigenvectors that for the original matrix. Okay, so the way we want to do this, we have the eigenvalues, and do you remember the procedure for taking eigenvalues to get the eigenvectors that correspond with them? Okay, I'll show you. So what we're gonna do, let's start with lambda equals 1. Okay, if lambda is equal to 1, do we remember that? Okay, well let's back up. Do we remember that eigenspaces are first and foremost just renamed null spaces?
Yes.
Remember that? Okay. Ergo, if I'm trying to find these vectors, what I'm really trying to do is I'm trying to find the general solutions to null spaces. Specifically, the null space is induced when I plug in my eigenvalue. Okay. So if my lambda is equal to 1, I am going and doing the null space. In general, I'm doing the null space of A minus lambda I, right? This null space is definitionally the eigenspace. Yes.
I was writing things down. Why did we cross those out?
What is 9 minus 3?
6.
What's 15 minus 9?
6.
So 3 lambda plus 6 and 3 lambda plus 6. Are those the same? If I have 3 copies of those and 3 copies, are they still the same?
That makes sense.
If one of those exactly the same thing is negative and the other one's positive, it cancels.
Sure.
Yep. Okay, so null space. Well, I know exactly which null space I'm interested in, right? Because I have my lambda. What's the lambda value I'm testing? Yeah, so it's just A minus I. Okay. So I'm trying to find the null space of A minus I. So what is my matrix A if I take away the identity from it? So go back to the original matrix and subtract out the identity. What's the first diagonal entry going to be?
0.
0, right? Because 1 minus 1 is in fact 0. And then we have minus 3 and 3. Then we have 3 minus 6, 3. What's the last column?
3 minus 3, 0.
Yeah, 3 minus 3, 0. Da, 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 da. Why am I augmenting this with the 0 vector?
The null space.
The null, right? Solutions of the homogeneous equation. So, solutions of this. Okay? and this is just an issue of row reduction, which I will not baby you over anymore. I'm going to swap the first and the third rows. So it's 3, 3, 0, 0, minus 3, minus 6, minus 3, 0, 0, 3, 3, 0. I do that because I don't want a 0 above any pivots. And then I think, wow, these are all just multiples of 3. Why am I doing 3? So 1, 1, 0, 0, minus 1, minus 2, minus 1, 0, 0, 1, 1, 0. And then I think even further, okay, well, let me get rid of this underneath my 1, right? And so I'm literally going to take my second row, I'll add it to this one, and then return it back. So my first row is unaffected, 1, 1, 0. So is my third row is unaffected. So this plus that is 0. Minus 2 plus 1, and minus 1 plus 0 is minus 1. At this moment, you should observe that we have exactly the same type of row. So one of them can go. The other one's going to be gone. And then I'll scale. So I basically have 1, 1, 0, 0, 0, 1, 1, 0, and a whole clean slate of zeros. Why am I anticipating at least one entire row of zeros?
Because we're looking for the null space for eigenvectors, which requires at least one free variable.
Because without that free variable, what are we missing?
A null space.
Non-trivial solutions. Yeah, we don't even have anything to put in it without free variables. So if you're doing one of these problems and you get no free variables, well then that's pretty indicative that your original matrix can't be diagonalized, right? Because then there are not going to be enough eigenvectors for you. So we're doing good so far. And the only thing we need to make sure is we get rid of the one above here. Because remember, if you're doing if you're trying to find the basis for a null space, you have to row reduce all the way. So the null space requires you to go all the way. That's very easy to do because it's just 1. So the second row is unaffected, third row is unaffected, and then I'll just take the first row and subtract that. So 1 minus 1 is 0, 0 minus 1 is negative 1, and we're done. Okay? So now we have this, which tells me some information. What is so I have x1 minus x3 equals 0. I have x2 plus x3 is equal to 0. And what do we call x3?
Free.
Yeah. Free. He's very, very free. Which tells me that I can write my vector x as x1, x2, x3, which is what?
X3.
X3.
And then minus x3, and then 1.
So if I factor out the x3, I get
1 minus 1.
and this right here is our corresponding eigenvector. Okay, so this guy, this eigenvalue, is tagged to this eigenvector. So we just keep that together in our head, right? Say, cool. All right, well, we have another eigenvector to test. And take a look at that multiplicity. What's the multiplicity of the second eigenvalue? Okay. Well, if the first, what's the multiplicity of the first eigenvalue? 1. Because, and then how many eigenvectors did I spit out? 1. Okay. So how many should we probably be expecting?
2.
We should probably expect 2. Why am I expecting that there needs to be 2? Because the multiplicity is 2. Yes. Okay. Lovely. This is so much easier. Why am I holding? I don't need this. Okay. Lambda is equal to 2. So it's your turn. I am now amanuensis of the classroom.
Oh, what?
And I will not write anything on the board unless prompted.
Me. Me. Big me.
Say it a little bit louder for everybody. Did everybody hear what Miss Rowan said?
Barely.
Okay, so you're gonna have to say it louder.
Far away.
For people in the back.
Equals null A minus I.
Are we sure about that?
No.
Chat, do we agree with A minus I?
It's 2. Because it'd be plus 2.
I totally miswrote the eigenvalue. Yeah.
Minus 2. Plus 2. It's minus 2. Plus 2.
Okay, what's the consensus? The null space of what?
Plus 2.
So A plus 2I.
A plus 2I. Do we know why it's A plus 2I?
Because the multiplexity value of
Okay.
lambda.
Okay.
So now let's write the A with the augmented thingy.
So we do a thing.
So let's
Do
put
the
1, 1, 3, 3 for the first row.
What?
No, I'm just copying. Oh, okay, you're writing that already. So it will be -1. Plus.
So we're gonna add 2 to all of our diagonal columns.
So it's 3.
What did you say,
We're
Sam?
gonna add 2 to all of our diagonal columns.
Why are you suggesting that, Sam?
Because
it's
2
plus
times
I.
the identity matrix is gonna give us 2's in our diagonal columns, and we wanna put that together with our A matrix so we can do null of A plus 2I.
Okay, raise your hand if you vote for that. Okay. So, tell me then, if we're gonna add 2 to all the diagonals, what is it gonna look like?
3.
It's all like a ton of threes.
And then 3. 3, -3, 3.
It's a whole bunch of 3s.
-3. It's almost like
There's all 3s. Yeah. So
You want to say that louder for the class?
This is 3.
Yes, I did say that.
Negative 3, negative 6. This is 3.
We never said
Ooh.
the augmented yet.
That's a.
Okay, what do we need to augment it with?
Zeros.
Zeros.
Allowing vectors.
We're gonna divide everything by 3.
Now we row reduce to 1, 1, 1, 1, 1, 1, 1, 1, 1. With negative and all the zeros.
Doing a lot of intermediate
It doesn't
stuff.
matter. -1, -1 is the same as 1, 1, 1 in this case.
Okay, Gloria, what do we do now?
1, 1, 0, and 1, 0.
So you're saying, what about these rows? Mm-hmm. Okay, so what's it gonna look like?
1, 1, 1, 0, 0, 0, 0, 0, 0.
Yep.
Let's see. Joshua. Interpret.
Interpret the.
Yeah.
You guys
If you don't know, bug Jessica.
X1 plus X2 plus X3 equals 0.
Wow.
That's a
Yeah,
Olamide, what do we call x2? I didn't ask you guys, I asked Olamide. It's okay. Olamide, what do we call x3? Bingo. Colby.
X1,
Minus x2 minus x3.
you pick it out.
Sam.
Which one?
X2.
Tyler.
X3.
Okay. So then I'll continue over here. Axel.
Then use with.
You take out the,
Agonal, help out your buddy.
X1 and then.
Where you getting X1 from?
Do we not have? Oh, my bad. I'm at X2
Okay, why am I pulling X2 out?
because it works.
It's
Yeah. Okay, Agonal, how does if I take the X2s out, what's it have to do?
-1,
then 1, then 0.
1, 0. And And then you take x3 plus x3. Factor out x3 stuff, and that's -1, 0, 1.
Bingo.
Dang.
So it looks like we have how many eigenvectors?
We have 2.
Is that enough?
That is
Yes.
enough.
That is enough.
That is enough.
Stand up and sing it, Sam.
Yeah, come on,
The
China.
whole song, the whole song.
There we go.
In
That's
the
what I
bridge.
thought. Okay. Okay. So if you can do these 2 steps, you're effectively good. Okay, because the way that you actually finish the problem is this.
I got some too, some.
Okay. So the last step,
Pretty.
final
All I know.
step.
Let me order.
They did tiny notes instead of pretty
Scott?
notes.
Can you just run through step 1 again really quick?
Yeah.
How do I read it?
To find eigenvalues of the
I
A
just
matrix
didn't want to
A,
use more than one this class.
then you need to take the determinant
I
of your
can read
A
it
minus
just fine.
lambda
I
I.
can write it too. It's just slow to write.
And then make sure we set the characteristic polynomial to 0.
trees.
And that tells me this.
What?
Is it because of cofactor expansion, or is it because of the concept of the determinant here? The cofactor expansion? Okay. Here's how the cofactor expansion works. I have my 1 minus lambda,
Yeah.
and then I've covered up this and this. Right?
Yeah, makes
So then all that's left is minus 5 minus lambda, 3 minus 3, 1 minus lambda. So that's what this is.
Yeah.
I alternate the sign. Where am I getting that 3 from? Well, it's because I'm going across the top row. So then my next term in the cofactor expansions is 3. And then if I cover up the top row and I cover up now the middle column, what's left is this minus 3 and 3 and this minus 3 and 1 minus lambda. So that's what goes in there.
Fair enough. Then you just reduce it.
Yeah. And then the 2 by 2 is simplified.
Yeah.
Okay, final step. So to construct my P, remember, remember the theorem that was written here? And there was this whole massive yappage, basically. And all that's saying is that you take your eigenvectors, and those eigenvectors are themselves columns of the P. So my eigenvectors of v1, v2, v3 is P. So what is P?
1, -1,
So let's take v1, 1 minus 1, 1.
-1, 1, 0. -1, 0, 1.
Denzel, what's the last column?
-1, 0, 1. I'm rocking.
Okay, so here's, and then now to construct the diagonal matrix, the entries of the diagonals will correspond to basically the eigenvalue that you got it from. So where did I get this first column? Where did I get 1 minus 1, 1 from?
1. Lambda equals 1.
Ta-da! I got it from there. So that corresponding entry needs to be the 1. So if the v1 is in the column 1 spot, then I need that eigenvalue to go there. I'm not allowed to just throw in my eigenvalues in any order whatsoever. Okay, they have to be exactly corresponding. Remember on the text wall it said like comma respectively blah blah blah. That's what that means. Like it to be with respect to the column. So then 0 0.
-2.
Let's see.
-2.
Wait.
Denzel.
So are you saying that because we put the first eigenvalue that's related to lambda 1 first, therefore
Yes.
we put
Because v1 came first as the first column, I want to make sure I'm putting the eigenvalue for v1 also in the first column. Ah. Okay, so Jessica, then what's the second column?
-2.
Yeah, but where?
Oh.
So
0, -2, 0.
good. And then what's the last one?
0, 0, -2.
Well, how did you know that?
Because the first eigenvalue vector is the one from step 2. And so that one is where we use lambda equals 1. So we put that in the first column, pivot point slot. And then the second column is respectively the same idea and concept. because we used it in the next step, and I'm really short, so I can't see it, but.
Oh.
And so then in the second column, we put -2 because lambda equals -2, and that's what we found for V2, and then V3 is also with -2,
Okay.
you know?
I'm gonna pause here and say this would be the most fantastic goated picture you could have in your phone and notes.
It's in my notes.
What?
It's got, what would be the title of the example? Like, what would the questions of the whole?
Well, what are we doing? We're diagonalizing A.
So diagonalize. Diagonalize.
Scott.
So whenever
What do
you
you
solve
want?
for lambda,
You
it's
do
not
everything
an
else.
array,
You know
right?
full
It's not
of
an
it.
array, it's just a random.
Ah, good question. I'll address that in a second.
Throughout learning how to factorize, that's all of this stuff.
Oh.
I can do everything else.
But how?
Okay. Now, a very, very excellent question has been asked. Miss Rowland, would you like to ask your question
Which
again?
part's the factor?
So when you're solving for lambda, you're just solving them randomly in a random order.
Okay.
So then how do you know the order?
Yeah, that part's easy.
So here's how we know.
You don't.
Let me clear some space. Okay.
Okay, I can explain it really quickly.
Okay, so if the eigenvalues are lambda is equal to 1 minus 2 and minus
Did you do
2,
this again?
it might have been like, okay, how did I know to do lambda equals 1 first? Fun fact, you 100% did not have to do lambda 1 equal first, okay? You could have done this in any order. Here's why. Think about it. Does it really matter? Are these two separate null spaces affecting each other? No, they just exist independently. So this solution set is going to happen no matter what if I plug in. And this solution set's also going to happen. So here's what we do want to be careful of. So say I had chosen to do this. Say I had chosen to do this one first. Then this would be considered my V1 and that would be considered my V2, right? So I would have gotten that one, then that one, and then that one, respectively to how it's been labeled, right? So then, what would the first column be of this version of P?
-1, 1, 0.
Right, so -1, 1, 0. What about the second column?
-1, 0.
-1, 1. And what's the last column? So now we're taking it, so this would be if we did in the other direction, right? So if we did this one last. 1 minus 1, 1. Now, did we break it? No, we didn't break it, okay? So all we have to do is when we construct D, we just emulate where did those come from. So this -1, 1, 0, I just keep track of the fact it came with my eigenvalue. So I'll put the corresponding eigenvalue with it. Okay, what about the second column? What do I do? What about the third one?
0, 1.
Fun fact, this shows us that diagonalizations are not unique. Okay? So long as there's this correspondence between the eigenvector with its eigenvalue, you're totally fine. That means there's another way we could do this. Okay? The lights can't even believe it. Okay? If I had done...
Just me.
Now, I don't recommend doing this because it would be a fairly foolish thing to do. But if I had chosen to split up my multiplicity and then go with like my 1 minus 1, 1, and then go, wait, no, I'm totally lying with you right now. Okay, so if I had gone with -1, actually even funnier, 1, 0, 1 minus 1, 1, minus 1, 0, 1. What is the necessary arrangement of my diagonal matrix to accommodate this?
-2, 1, -2.
Okay, so -2, 1, -2?
-2, 0, 0, 0, 1.
Yeah.
You knew what we were saying.
0, 0. What about the second?
0, 1.
Okay. 3 diagonalizations.
For 3 eigenvalues.
Okay. Now, here's how you would, just so that it's been taught, if you want to check, so sometimes it's kind of difficult to verify it using the original. So what you can do instead is use the thinker for 2 seconds and go, I'm too lazy to actually figure out the inverse situation. So what I'll do is I will multiply both sides of this by p. So I get AP, trauma for all of you overachievers in high school, equals PDP inverse P, which is just PD. APPD. There's a lot of different cultural associations with both of those. So anyway, if you ever need to verify a diagonalization, you can always compute AP and then PD separately, and so long as they're the same thing, that means this checks out, okay? So that keeps you from having to solve for an inverse, because frankly, I don't even want to solve for an inverse. And when I was making the lecture notes, I thought about it, I was like, no, I'm not going to do that. So AP equals PD is the way to go if you want to verify this. Why is this a great verification? The diagonal matrix, these are super easy to multiply out, because guess what? As soon as you hit the one value, cha-ching, cha-ching, everything's 0, right? So it's very, very easy. And then this is the only one that's kind of like, It's
You gotta do what you gotta do.
Now, let me think if there's anything else that needs to be said. So, what we're definitely not going to do is not forget that you took notes on this example.
I took notes.
And we're definitely not going to forget how to do it.
Right.
Yeah, Sam?
Okay, so our final step is just finding P and D.
Yep.
So that satisfies finding our diagonalization of A. We don't also have to find our inverse of P.
Correct.
Only if we needed to verify.
Yeah, so verify. Once you verify it, then you can start doing some crazy stuff, right? So hear me out now, right? If then you were asked to compute A to the, let's think of something gross.
Negative 13.
1.
Oh.
That is gross indeed.
Don't do it. Don't do it. Love you.
Power.
Right?
1,000.
All you have to do
Yeah, that is
It's big.
is find P inverse, and then you don't actually have to exponentiate your P or your P inverse. The only thing you're exponentiating are the diagonal entries. In that case, you could just put 10 to the 12 power. Okay? I'm not going to do that again, because the repeating exam questions is not only unoriginal and boring, but a sign of lack of creativity and therefore lack of intelligence. And so I would not do such a horrendously insulting thing. That wasn't sarcastic. Okay. Okay. So that it's been communicated, I would like really strongly recommend like knowing this. Okay. Perchance, right? Like if I go to do this example for the lecture and think to myself, wow.
So when you're thinking about that, what question are you thinking about in the exam?
Huh?
Make this 60%
When
of
you're
the points
thinking
of the
about that,
exam.
what question on the exam are you thinking about making?
Is that really that important?
What?
I'm just curious.
Minus the fact that you already know.
You should make it. You should make it question 3, so you have a whole bunch of 3s you can do.
In theory, if this were question.
Hypothetically, right,
if
yes.
you're asking us to find A to the 1 trillion.
Very hypothetically.
If, would you accept 1 as the answer? Would you want us to put 1 to the 1 trillion?
Well,
1 trillion is still 1.
counterpoint. If it's an objectively correct answer, can I mark it as wrong?
No.
So, yeah, you get to say 1.
Okay.
Now, typically, and the thing is, don't just, and I'm gonna warn you, don't brute force think you can just brute force memorize the whatever. Because if you don't truly understand the step, then if, say, you're given like a shortcutted or abbreviated version, that you're not thrown off by the fact that it doesn't look exactly the same, and that you could still pick up and finish, okay? So, what's the point of what?
To the A to the 1 trillion.
Oh, the point of that is now if you needed to feed this into a computer, instead of making the computer read that and power it up, it's only reading this and powering it up. And then then you take the pin. Okay, you're free to go. Enjoy your spring break.
Enjoy it.